Okay, so here I wanted to go over a question that involves banked corners or banked turns. So what we see here is like a car driving away from you on a banked corner, and the question could be, say, maybe question: how fast can the car go around this turn? And let's say the radius of this, so I'm telling you the mass of the car, the angle of the bank, the angle of the corner, and let's say the radius of that circle is, say, I don't know, like 80 meters. So the question is, can this thing go around, then we'll assume friction, like force of friction, 0. Mu is 0. So the only thing that can help this thing go around the corner is the bank itself. So the first thing I would do is we have to draw a force diagram. So I'll first draw the forces on the diagram, the drawing, and then I'll do a force diagram. So there's Fg down, and then actually the only other force acting on this is the normal force. So that's it. So let me redraw the force diagram over here. And so in order for there to be circular motion, we need a force that's pointing towards the center of the circle. And you could say, well, Fg is not pointing towards the center of the circle at all, but, sorry, that's supposed to be an N. But there is a component of this force, normal force, that does point towards the center of the circle. That's this bit right there. We could call this N, I'm going to call that N, what do I call it? Call it NX, I guess. And this is NY. And this is, that small angle there is your 25 degrees. And I can tell just because kind of looking at this drawing here, clearly this is a really big angle, that's a small angle, so that must be the 25 degrees. So looking at this diagram, we could say, if we're looking for the F net equation pointing towards the center of the circle, Fc is equal to Nx. It's the horizontal component of that normal force. So we don't know that yet, but there's one thing we do know, and that's Fg. So Fg is equal to mg. So Fg is equal to 1,500 kilograms times 9.8. So I'll put that in my calculator. And I get 147. Okay, so we know Fg. We also know that this car is not rising up into the air or sinking down into the road. Therefore, we know that vertically the forces are balanced. So therefore, we know that Ny is equal to Fg. And that's the 1,470 newtons. Aha! So now we can get somewhere. We know Ny, we know this angle, so we can get Nx. So we know that tan 25 degrees is equal to Nx over Ny. So Nx is 1,470 times tan 25. So the horizontal component of that is 6, is that right? I feel like, oh, sorry, there's another 0 here, that's why. So that is 6.855 10 to the 3. Okay, so we now know, and that's equal to the centripetal force. We're still looking, though, we're looking for how fast can that car go around the corner. Well, we know that Fc is equal to MAC, and we know that we could also rewrite AC as V squared over R. and that is equal to 6.855 times 10 to the 3 newtons. So V then is 6.855 times 10 to the 3 times the radius of the circle, which is 80, divided by the mass, and then square root. So I'll take that number, times it by 80, divide by the mass, square root. So this car can actually go really fast. That's 19 meters a second around the corner. So even if there's no friction, that car can go 19 meters per second around the corner. That's how you do banked angled circular motion questions. Just a thing to take note here, we could do this problem without even knowing the mass, because the question started by using the mass in a calculation for FG, but at the end we divided by the mass. So let me just see if I can work out what this would look like if we didn't include mass. So FG is equal to mg. Then ny is equal to FG, which is mg. And x is equal to mg times tan theta. That's this part right here. So that's also equal to FC. So FC is mg times tan theta. Then that's equal to MAC. So we have m times AC, which is m times v squared over r, and that's equal to mg tan theta. And those masses cancel out. V equals g tan theta times r square root. So I'll just double check that works. So it's 9.8 times tan 25 times 80 square root, and let's just hope we get 19. Works. There you go. So this is a good, also a good example showing how you could solve a question like this even if you don't know mass, and also a good example of how you can solve problems by plugging numbers in only at the very end. This is a skill to get good at. Yeah. If some of you are interested in going to post-secondary school and maybe going to engineering type stuff, the more you can deal with using equations without plugging in numbers, the better off you'll be. If your plan is to go into engineering and that's the goal, then your goal right now should be to get better at things that will help you be successful later on. That means your goal right now should be to start doing this, regardless of how hard you think it is right now. This should be your goal, if that's kind of where you're thinking about going. All right, there you go.